Hi, this is Ryan Linfield. I just want to do a quick demonstration of buffer overflows. I'm calling this a crash course on crashing. So let's go ahead and get started. We know that a computer uses a CPU to handle instructions. Anytime we've got multiple processes running, those processes are typically competing for a time slice of the CPU. When the CPU is executing instructions, he uses different registers so that he knows how to operate on a program. So a register is something that the CPU has, and he has a number of registers. There's different types of processors, Intel, PowerPC, ARM, Spark, etc. Different types of processors have a different quantity of registers. What we're really focusing on today is going to be x86, and we're going to look at three particular registers that are special because they help support the stack. So at this point, we know that the CPU uses registers, and we know that there's a couple particular registers that he uses to monitor the stack. So let's take a look at what the stack actually is. When you look at the total amount of memory that you have available, let's say that you bought a new laptop and it has 16 gigabytes of RAM. Well, that 16 gigabytes is basically being utilized or shared by lots of different applications. Whenever an application grabs some memory and starts loading pieces of the program into it, that collection of memory is referred to as the stack. So if you've heard there's a paper called Smashing the Stack, which is one of the original papers on buffer overflows, that's what they're referring to. So our stack is a subset of our totally available memory that's being used by a particular application. Now, the stack is very organized and it's structured. You see, you start off with a value called your base pointer, or EBP. The base pointer is also a register that's down here, and that register is pointing to the base of memory, or where does this application actually start. On the far end, the opposing end from the base, you have what's referred to as the stack pointer, or ESP. This is also known as the top of the stack. So throughout the operation of a program, sometimes the program does different things where it uses more memory, and sometimes it does things where it uses less memory. In terms of a web browser, think that you're opening more tabs and you're loading more web pages. As that happens, your memory utilization goes up. If you look at your Process Explorer and you see that Firefox, if that's your browser, is using 380 megs of memory, you go, man, that's a lot of memory. You start to close those tabs out, your stack pointer comes backwards towards the base and you use less memory. So throughout the life of a program, that base pointer stays in the same location. He's referencing a particular memory address. The stack pointer is counting away or counting back towards the base pointer, depending on whether we're actually growing or shrinking. As new things are added, they're said to be pushed to the top of the stack. That's a push. And as things are removed, they are popped from the stack or removed. So pop is to take away, a push is to add. These are two very basic assembly instructions which have to do with the stack maintenance. Within this stack, we're actually executing instructions, so there's different things that are happening constantly. There's a third pointer, told you there's three that are special, and that third important pointer is called your instruction pointer. So we've got EBP, which is our base, ESP, which is stack, and EIP, which is the instruction pointer. This is the actual code to execute. So I'm just going to put EXE here because this is the next thing within the stack that'll be executed. What's dangerous here is we also have a buffer, and the buffer stores user data. So some of the data that exists within the stack, it could be Internet Information Server, or IS. It could be Apache. So you have all these modules or DLLs that are used by the program. You have memory that the program actually requires to run, and it's right alongside of programs here, or content that's actually being supplied by the user. So in the context of a web server, I'll put web server, WS, over here on the left. And web browser, just to the right of that, the conversation that a web browser and a web server has, the web browser sends a message to the web server. A lot of times it's a GET request, and we're requesting a particular resource. That resource that I'm asking for, maybe it's index.html. This request needs to be placed inside of a buffer. That buffer lives inside of the stack, and the application takes a look at this. Let me draw some eyeballs here. We're taking a look at what's actually in this buffer so we know what to process next. The danger of buffer overflows comes from unchecked user input. If there's a simple line of code here that basically says take whatever the user supplies and place it in this buffer. And you see how vague that was? We didn't really talk about if it is ASCII characters, and if it is more than 10 but less than 100, place it in the buffer. There were no bounds. There's no bounds checking. We just said take whatever the user supplies and place it into this buffer. Well, without doing any checking, let me switch over here to red. What's going to happen is this buffer will fill, and it will actually go beyond the boundary of what's supposed to be for the buffer, and it can overwrite the portions of memory that our instruction pointer was actually pointing to. So the way that this works in an exploit is we actually shove executable code into memory, and we take this instruction pointer, and I've always thought of this as like a record needle, and I basically get it to execute some other process. Well, in order to do that, we have to fill the buffer, and we have to begin our executable code, or op code, exactly where that instruction pointer is. What I'm going to show you today is just how to do a buffer overflow. So I want to fill this with garbage. I'm going to use the hexadecimal representation of the letter R. Why R? Because, well, my name's Ryan. I want to try to process, let's say 3,000, maybe a little bit more, 3,000 R's in a row. I want to shove that into the buffer and see if the web browser, or the web server is doing any type of sanitation where it's stopping me from shoving this huge quantity of R's in, or if I can just shove them in all at once. So the way to actually inspect this, I'm going to bring up a Windows host, and this is just a Windows XP Service Pack 2 host. It's one of the easiest operating systems to actually look at applications within. And we're going to open up OllyDbg. Now, I come from a network background, and I've learned so much about networking using Wireshark. Well, I think of OllyDbg as the process equivalent of Wireshark. So we use Wireshark to look at packets. I can use OllyDbg to look at a process. So I can open Minishare, which is a web server. This is what it basically looks like now. And what we're looking at here within OllyDbg is that we have 4 windows. What you have on the left is CPU instructions. So we've got memory addresses, we have opcode. Like one of the famous opcodes is you'll see 0x90. 0x means it's hex, 90 is the opcode for no operation. This is used in NOP sleds. You've got moves, you've got inserts, you have adds, you have jump to non-zero. You have all these different assembly codes. Now, this isn't a class on assembly level programming, but Minishare, my HTTP server, this is what it really looks like. Like you've looked at source code before, this is the assembly code. So it's a little bit rougher on the eyes than looking at traditional C, but this is what my program looks like. Now over on the right side, we have our registers. The CPU has different registers. We mentioned that there's a stack pointer here. We mentioned that there's a base pointer there, and then we've got the instruction pointer, which is the actual entry point. This is when we launch the program. That's where it's going to start. So I'll go ahead and hit play. And you saw that those values changed and it hopped around. That's what happens when the program actually launches. So here I've got this program up and running, and if I come over to my web browser, here, let's just make sure that I can refresh it. There we go. So my web server's up. It says you've reached my Minishare server, and it's simply sharing a document here called report.html. If I was to click this, my web browser, which is Firefox, is going to send the web server, which is Minishare, an HTTP GET request for report.html. And if I click on that, it comes up, nothing special there. It's just an HTML document. What I want to do is something a bit more mischievous. I want to do an HTTP request for a string of 3,333 capital R's. So the way that I do that is use Python, and I'm going to create a TCP socket. I'm going to connect to 172.16.123.133. That's the IP address of my web server. I'm going to connect on port 80. Once I get there, I've got a buffer that I'm creating locally that says send a GET request, followed by, in this X52 here, this is the hexadecimal representation of an R. there's different ASCII codes and hex codes which can represent different symbols. So like a 41 is a real common use for like NOP sleds as capital A. Just to make it a little bit more interesting, I decided to use an R because my name starts with R, looked it up here, and it's a hexadecimal 52. So coming back, we see that I'm going to create 52 times 3,333s, and this should be in an HTTP format. I'm going to send 2 returns afterwards. So the way that I would run this is just like a typical script, and it immediately returned. Now, my script here doesn't really echo any output. It's not like the server has crashed or it worked, but if it couldn't connect, it would just have hung there. And if it did connect, it just closes out successfully, and that it did. So let's take a look at our Windows host here, and we see that it's paused. And we go, oh, that doesn't look good. Over here in our registers, we see that our stack pointer is overrun with this string of capital R's. What does that actually look like? Well, here we see all these 52s at all these different memory addresses. So this is me shoving garbage into the buffer. In this case, my garbage was 3,000 R's, and it didn't do any type of input or boundary checking. So it overflowed the buffer, it overwrote the rest of the stack. We see that my instruction pointer here is 52, 52, 52, 52. Not useful. It didn't give me a command prompt. It didn't give me any passwords that the user is using. It didn't steal their sessions or their cookies. This was simply a buffer overflow, but this is the first level of injecting the code that we actually want into memory and getting it to execute. Now it says that mini-share is still here, but it's locked up. It's not responding. I see the icon down in the bottom right, and it's red until someone connects. Once they do connect, it goes green. But you'll watch when I mouse over this and I try to interact with it, it's non-responsive. So it's just completely crashed and locked up. This isn't really exploitation, it's just causing an application to crash. But it is the first step of exploitation. What we're going to do in future episodes is take a look at how to predict how many capital R's did I have to shove into the stack before I actually overwrote this instruction pointer. And what I can do, if we go back to my crude illustration here, is I can actually put, let me just go ahead and change my color to green here. Something that I did want to run in memory, I would fill a bunch of garbage here to fill this buffer, and then just after it, I would put code that I want to actually run on that host. So if I want to put a backdoor in there for a rootkit, if I want to set up some type of relay so that I can tunnel traffic through this user, I could do that. But the first step is finding a vulnerable application. The way that we discover vulnerable applications is by fuzzing or simply shoving in malformed queries or weird things that shouldn't happen. You know, no one should send 3,000 capital R's to the web server and request that. And if the web server code was written a little bit better, you would have seen that get rejected. But it wasn't. They didn't do any boundary checking because it takes more time and it takes more work. So web applications, a lot of times they can be found all over the place. My DVD player has one. My receiver has one. We've got video cameras in our home. We've got printers. There's web servers everywhere. Most of them are very, very insecure. The way that we can test to see if they're doing any type of boundary checking is just like you saw here today. Simply go ahead and connect to it using something like a Python script, shove in a bunch of garbage, see how it behaves. In this case, I've found a vulnerability, and all I have is denial of service. I could have this little script that throws a bunch of capital A's there and it crashes the web server. In the hacking world, unfortunately, denial of service is pretty lame. What would make it a lot cooler is running my own code from memory through the use of a buffer overflow, and that's what we'll do in our next section.